Hello, this is Mr. Collier, and today we're finding general rules from diagrams. So let's take a look at the first example. It says continue the pattern for two more figures. Well, we have one square, two squares, three squares. So the next one's going to have four squares. But as you're doing it, you want to keep track of what you're actually doing. So to get another square, notice that I'm adding three more line segments or three more matchsticks or whatever to the pattern. So I have 1, 2, 3, 4, and I added three more line segments here. Okay, so the same thing's going to happen again when I'm going to the next one. So you want to do this part really slowly to see what's really happening, because now when I get to this point, I'm going to add on my new part, and I'm adding on three more line segments. So that's going to be key in explaining the general rule a little bit later on. Okay, so that's part A. Part B, describe the pattern in words. So describe the pattern in words, you could say, as you add each new square, you add three more line segments. Okay, so you can describe it that way. Part C, set up a table to represent the results. You need to define your variables first, dependent and independent. So we're going to set up a table. We're going to have number of squares. Let's call that S. And we have 1 square, 2 squares, 3 squares, 4, 5. As far as our diagrams go. And then we'll call this line segments. We can't use S, so let's call L for line segments. Okay, so S equals the number of squares. Okay, and is that dependent or independent? We'll just take a look at that in a second. L is number of line segments. And how do we determine which one is the independent, which one's dependent? Well, one clue is usually the independent is going up by a constant amount each time, so it's going up by 1. And what happens is the number of line segments depends on the number of squares. If I've got 3 squares, then I can determine how many line segments there are. If I've got 1 square, I know there's going to be 4 line segments. It all depends on how many squares you have. So the dependent variable depends on the independent variable. So this one is independent, and this one's dependent because it depends on the number of squares. So continuing my chart, for 1 square I have 4 line segments, and then I got to add 3 more on here, so that's 7. And you can see I'm counting 3 more each time. So that's going to be 10, 13, and 16. Okay? So I filled out my chart. I defined my variables. Now to describe the general rule. Describe the general rule. We're going to use this fact that I was adding 3 line segments each time, and that in my chart you can see that the common difference is 3. Okay, so that means I'm adding 3 each time, so I'm going to be multiplying 3 times the number of squares, and that's going to be equal to the number of line segments. So the number of line segments equals 3 times the number of squares. And does that work out? If I do 3 times 1, do I get 4? No, I need to add an extra 1. Okay, so L equals 3S plus 1. 3 times the number of squares plus 1. And it works. You can check it for 5. 3 times 5 is 15, plus 1 is 16. Okay, you can try extending your graph and try and predicting what's going to be next. So I put 6 in my formula. We have L equals 3 times 6 plus 1. That equals 19. I should get 19 when I extend this chart, and I do get 19 when I extend the chart. So it seems our formula works. Part E is explain why it works. And that part, we need to talk about the geometry that's going on here. We could say let's see, I don't have much room. Let's make a little bit more room. So you can say for each square you add on, you use 3 more line segments. Okay, in other words, you're using 3 line segments per square. That's why it's 3 times s. And you can show this geometrically, maybe right here. I'm going to show it right here geometrically. So that's my initial value. So for each square, I'm using 3 line segments. 1, 2, 3. And there's 1 left over at the beginning because the first square used 4 line segments. So that's where the +1 comes from. So we need to clearly explain that. Okay? So I can show here that, okay, so I'm going to show that I'm adding 3 line segments for each square. Okay, and 1 extra line segment goes with the first square. Okay, therefore the number of line segments equals 3 times the number of squares plus 1. Okay, you can even use a highlighter and show, oops, I better fix my mistake there. That's 3s plus 1. Okay, we can use our highlighter to show that this, actually I'm going to highlight that green, just like I used over there. I'll show that that 1 extra line segment comes from there, and our 3, well, I'll use yellow, 3 comes from the 3 line segments that you're adding each time. So let's take a look at another example. Continued pattern for 2 more figures. So we have a bunch of triangles here. Next figure we're going to have, okay, we're going to have a triangle, another triangle here, another triangle. And here's a new bit. I like to do that in a different color. I'm going to add on 1 more triangle. Oops, it's not a new color. So I'm going to add another triangle, but I'm really adding on 2 line segments. Alright, so I'm going to add another figure to the pattern here. So I'm adding this, adding that, and my new bit is going to be 1 more triangle, but it's just adding 2 extra line segments. So those are the next 2 pictures in the pattern. And we'll describe the pattern in words. You could say for each new triangle added, you add 2 line segments, or matchsticks, or whatever we're talking about here. So for C, we're going to set up a table. We can have number of triangles, T, and the number of matchsticks, or we'll call line segments again, L for line segments. Okay, so number of triangles is 1, 2, 3, 4, 5. Number of line segments in the first one is 3. In the second diagram, we're adding 2 more on, so that's 5. Then we add 2 more on here, that's 7. So it's going up by 2 each time. You show that in the diagram as well as +2. Show that in the chart, +2 each time. Okay, so our variables are t, which equals the number of triangles, and L is the number of line segments. Okay, so the t-value of the number of triangles, that could be any number. It's going up by ones, and it does not depend on the number of line segments. The number of line segments depends on the number of triangles. So that would make this, the number of triangles, the independent variable, and the number of line segments, the dependent variable. So part D, find the general rule. So for part D, we know we're increasing by 2 each time, and we can see we're increasing by 2 each time in the diagram here. So that corresponds to 2 times the number of triangles in our formula. So line segment equals 2 times the number of triangles. Does that work for 1 here? 2 times 1 is 2. We need to add 1 to get 3. 2 times 2 is 4. We need to add 1 to get 5. So it looks like that has to be plus 1. We can show that we can predict for 6 triangles. It should be L equals 2 times 6 plus 1, which equals 13. And it is 13 if you continue the pattern on the chart. So it looks like our formula works. And for part E, we're going to explain why it works. We're going to talk about the geometry behind the pattern to explain why it works. Okay, so we can show that we get 2 of the line segments from each of the triangle. Each triangle, we get 2 line segments, plus there's 1 at the beginning. So we get, alright, we get 2, a little bit harder to show. Maybe I should alternate colors. Maybe that'd be better. So let's do that. So I'm completing my triangle with 2 line segments. I'm using 2 more line segments and 2 more line segments, 2 more line segments, oops, and 2 more line segments. So to make a new triangle, I'm always adding 2 more line segments, except there's 1 extra one at the beginning. Okay, so explain how the rule works. You could say, you can show it like this. Maybe I'll do that in blue. Okay. You can say for each triangle, you add 2 new line segments. So you have to multiply, multiply the number of triangles by 2 and add 1 because of the extra line segment in the first triangle. So we can see that let me highlight that in yellow. So that's and I should probably put a plus 1 there too. Show that there's a plus 1 there. Right? And I'm going to highlight that in yellow too to show that's where that came from. And I've got another color highlighter here, so this is the plus 2 each time. And there we go. So this shows that you're adding 2 for each number of each triangle, so you have to have 2 times the number of triangles. And I'm going to rewrite the formula here as well. So L equals 2 times the number of triangles plus 1. That plus 1 comes from that extra 1 at the end. And the 2 comes from your constant rate of increase.